Good morning. I'm Jun-Seok Bae from Australia. First of all, it's my great honor to be one of the recipients for 2021 COFST Award. Also, I would like to thank Korean Scientists and Engineers Association in Singapore for giving me an opportunity to talk at AKC 2021. Let me share my screens. Yeah. All right. My talk today is about enrichment of ventilation air and methane, so-called VAM, covering the journey from laboratory studies to site trials. Firstly, I will talk about a little bit of myself, then covering some backgrounds for those who are not familiar with VAM. Understanding the characteristics of VAM would lead to feasible options to mitigate and utilize VAM. Amongst the available options, my talk will focus on global efforts to enrich VAM. Who I am? Well, I came to Australia to obtain a PhD in 1999, which was my first overseas trip. Ever since then, I've been living in here, Australia. In 2004, I received a PhD in chemical engineering at the University of Queensland and then worked for a while before joining CSIRO in 2010. Personally, I'm a bike rider. Actually, last Sunday, I rode 100 kilometers from Brisbane to Gold Coast with an average speed of 33 kilometers per hour. And also, I'm a tennis player. I have won some competitions. Publicly, I'm a AKC Queensland chair. Especially, I was a local chair of 2018 AKC in Brisbane. CSIRO stands for Commonwealth Scientific and Industrial Research Organization, which is one of the most multidisciplinary research organizations in the world, with a staff located at many sites throughout Australia and 3 overseas. I'm based in Brisbane, one of the sites in Brisbane, Queensland. All right. There is a term called coal mine methane, CMM, which is methane gas produced or emitted during coal mining operation. Methane gas is a safety hazard to miners and also a greenhouse gas, a global warming potential of 28 to 36 over 100 years. Also, methane is an energy source that can be utilized. There are main 3 CMM sources. Prior to mining, you need to drain for safe operation. So that methane gas concentrations are between 60 to 95%. During the mining, also, you need to drain the gas. So that's typically 30 to 95%, depending on the site specifications. The last one is you need to supply ventilation air for miners underground. So typically that's ventilation air contains less than 1% methane. The first 2 sources can be directly utilized for power generation, but the last source, however, has been an ongoing challenge to mitigate. Fugitive emissions account for gases that leak or vented out during the processes in relation to fossil fuels, such as coal, crude oil, and natural gas. Methane in ventilation air from underground coal mines is the major emission source of coal mining activity. This is the main reason that we focus on VAM to reduce greenhouse gas emissions. Firstly, we need to understand the characteristics of VAM to deal with. Ventilation air has huge and variable volumetric flow rates. In typical gassy mines, ranging from 120 to 600 cubic meter per second, and also very dilute and variable methane concentrations from 0.2 to 1% in air. And also there are some CO2 in presence. And also that ventilation air contains lots of moisture, and also it's very high relative pressure, relative humidity. So almost 100% saturated. Then also ventilation air contains dust particles, as you can see in this SEM image, the particles, dust particles. So the photo in the right-hand side shows ventilation shaft with the suction pumps taking air from underground and vent it out. So once the characteristics of VAM are understood, how do we mitigate VAM? There are typically three options. Firstly, VAM can be oxidized as a primary or supplementary fuel. Basically, methane is converted into CO2 to reduce greenhouse emissions, gas emissions. Secondly, it can be utilized for power generation. The last option is to capture and enrich to a certain level so that other mitigation units can utilize. At CSIRO, all three options have been investigated and site trialed at an Australian coal mine. The first photo shows a prototype unit to oxidize VAM directly. And the photo in the middle is a power generation unit that requires a constant methane concentration in the feed stream. So it can generate about 25 kilowatt. The last one is a VAM enrichment unit that I designed. My talk today is about VAM enrichment unit and how we developed whole process. So what was the motivation for VAM enrichment? Here are some key motivations. As I mentioned before, for power generation units, a minimum methane concentration is required. For this reason, a supplementary fuel is typically required for self-sustainable thermal balance. And also for stable operation of mitigation units, we need a stabilizing mechanism to ensure stable operation and minimum maintenance for continuous power generation. So it's acting as a buffer. And also, VAM enrichment offers more greenhouse gas emission reductions than simple oxidations, because simple oxidation generates CO2. Now, before we talk about the available VAM enrichment technologies, operational safety at mine sites is the priority. We need to eliminate ignition sources. Also, a methane explosive range is between 5, if you can see this graph, between 5 to 15. So we need to avoid this range. In the course of any VAM enrichment process, we need to avoid this range in gas phase methane. In addition, it will be good to keep the oxygen level below 12, so it's safer to operate. So there are several options to enrich VAM. Hydrate formation requires pressurization, having slow kinetics and low methane recovery. And the liquid ionic liquids, where CO2 preferentially absorbed over methane, and it requires long gas-liquid contact time. So you can imagine the design, the size will be huge, bigger than the other process. And membrane separation, still the membrane itself, the low selectivity over other gases. And also we need a pre-treatment to remove dust. So that requires more capital and operational cost. Considering the above requirements and our previous research, adsorption-based processes with solid adsorbents are the feasible and proven technology that we have been focusing on. Let's talk about adsorption-based processes with the solid adsorbents. Two research directions: development of process, how we capture and dissolve the captured methane, and how do we operate. And also, we need to make good adsorbents to deal with the characteristics of VAM. So that's we at CSIRO, we have been investigating both sides. Now, in this graph, we can change the temperature from here to there to obtain to capture and to capture the methane from ventilation air. And also you can change the pressure so that either it can be vacuum swing adsorption or pressure swing adsorption. Still, you change the pressure so that the swing process involves changes in temperature and pressure. So initially, the adsorbents needs to have a high methane adsorption capacity, of course, and also you need to have a high methane selectivity over nitrogen and oxygen. Also, we need a fast adsorption and desorption kinetics and adequate mechanical strength and the chemical stability and tolerance, especially moisture. There is moisture in the ventilation air, so it should be negligible on the methane capture capacity. And also, the regeneration energy is the main source of energy consumption for this process. So you need to minimize the regeneration energy. And of course, the adsorbent cost we need to consider. So the swing processes, VSA, vacuum swing adsorption, temperature swing adsorption, you can, or pressure swing adsorption, you can combine three or both, or yes, you can combine VSA, TSA, and PSA. So depending on the target components and depending on the characteristics of the mainstream. The gas adsorption capacities of any solid adsorbent should be considered at relevant partial pressure rather than ambient pressure. The effect of moisture should be tested also to be negative, or no, sorry, to be negligible for VAM enrichment. Remember that ventilation air contains almost 100% humidity. Also, adsorbent should be in structured form, either in pellets or monolith for scale up. If you have a powdery samples, it's hard to scale up, and also lots of engineering issues during the process. Suppose we have 3 samples. Here, A, B, C. If you look at the adsorption capacity at 100 kilopascal, which one is best? Of course, sample B. Sample B is best. But if you look at the relevant partial pressure, which ranges from 0.3 to 1 kilopascal, of course, sample A is the best. So this is confirmed by looking at the pore size distribution. On the right-hand side, sample A has higher peaks of pore sizes less than 6 angstrom. So you can either check with the pore size distributions at this range or the adsorption capacity at relevant partial pressure to select the best adsorbents for VAM enrichment. So at CSIRO, we have been developing carbon composites to meet the requirements that I mentioned before. And as you can see from the graph, CSIRO's carbon composites possess more than double times of methane adsorption capacity than the commercial activated carbon. So if you look at I didn't show here detail, but if you look at the low pressure range, it's more than 2 times. So we made a carbon composites in a honeycomb monolithic structure to deal with the high dust environment and to reduce pressure drop at the lab small scale. We look at the detail compositions and also in the laboratory study with the breakthrough tests. And also we improved the methane capture capacity by using bio-waste such as Macadamia Nut Shells. So that's, it's about 40% of world macadamia are produced in Australia. So the Macadamia Nut Shell contains low ash content, lower ash content than other nut shells, possessing high methane adsorption capacity. And also we have tested the moisture effect on methane capture capacity, and we found negligible. You can see here we improved from carbon fiber composites and then Macadamia nut shell derived composites. So we improved the breakthrough time, which means the performance capacity increased, but still the moisture effect is negligible. If you look at the low pressure range, we improved about 35% from the carbon fiber composites previously we made. So that's Macadamia nuts in tree, and this one is a shell. So we grind and carbonize and made composites with other ingredients. Along with the adsorbent development, suitable processes where we investigated. There are many two processes that have been used for VAM enrichment. First one is a vacuum pressure swing adsorption. It's called the VPSA. So University of Science and Technology in Beijing enriched VAM from 0.3 to 7.73%. And another university increased from 0.42 to 1.09%. At CSIRO, we used vacuum temperature and vacuum swing adsorption process. So we can enrich 5 to 11 times. And also we can regulate how much we want between 5 to 11 times by regulating the vacuum pressure. So that's 5% enrichment on average. On the right-hand side, the figure shows 11 times enrichment on average. So which is the world's best result. For the process level, we made a large carbon composites in rectangular or cylindrical shape. The length here, from here to there, about 10 centimeter. The width is about 3 centimeter. The length we made, or the height is about 20 centimeters. So this is slightly bigger. The basic idea of VTVSA process is that the initial vacuum removes mostly nitrogen and oxygen from the composites because of the affinity of methane greater than the nitrogen and oxygen. And the composites are heated up to dissolve the captured methane. And finally, we applied a vacuum again to take the dissolved methane out of the composites. So we developed a single stage and two-stage processes. The photo here shows a single stage unit that I designed. So as I mentioned, the single stage process, we can do that 5 to 11 times enrichment. And with understanding the result from the single stage processes, we designed a two-stage process to operate in a safe manner at the coal mine sites. What makes our technologies unique is that the enrichment process is out of the methane explosive range, increasing methane concentration from less than 1% to less than 5% through the first stage. And then increase methane concentration through the second stage to over 20% or 25%, depending on the initial vacuum pressure. So we can regulate initial vacuum pressure to meet the gas phase methane to be less than 5% after the stage 1. And then it jumps to the over 20, 25%. So in the stage 2, this is in adsorption phase. So it's safe, as long as it's not in the gas phase, it's safe to operate. So currently, it is a batch system that its mass transfer zone is somewhat diluted. So these performance can be improved if we operate in continuous mode. So this is a two-stage VTVSA process unit that I designed. So this unit went to the site and we tested. So as of today, 2 processes have been site trialed. The first one is at Julong mine site in China. They used the coconut shell activated carbon, a 2-stage vacuum pressure swing adsorption process. The treatment process, the capacity was about 500 cubic meter per hour. The enrichment performance from 0.2 to 1.2%. So they operated in the continuous mode. Whereas at CSIRO, we used carbon fiber composites with 2-stage vacuum temperature and vacuum swing adsorption process. So treatment capacity is smaller than the Julong mine site. The enrichment we obtain with the real VAM from 0.58 to 28%. And because the VAM concentration varies, this is the averaged one. So 0.73% to 32%. So that it can, as I mentioned before, we operate in a batch mode. So if we operate in a continuous mode, we expect this performance would be improved better. So that's the current stage, and we can develop further with the continuous mode on this unit. So in summary, mitigation of VAM is an ongoing challenge due to its intrinsic characteristics. VAM enrichment, in terms of VAM enrichment, adsorption-based technology is the way to go. We have been studying in this area for many years. So our conclusion is the adsorption-based technology with the solid adsorbents. So adsorbents needs to be structured and tolerant to moisture and dust environment. That's why we chose a honeycomb monolithic structure that can be applied at the mine site. CSIRO developed the world best results with the single and two-stage vacuum temperature and vacuum swing adsorption processes. Also, we successfully demonstrated their technology in a safe manner at an Australian mine site. We went through all the mine site and regulations and standards for site trials. We made it successfully. A special thanks goes to Dr. Shisu, who leads the emissions abatement team in CSIRO Mineral Resources. His dedications to VAM research is well recognized in this area. Also, I would like to thank his team members, including Shin Yu and John In, for their support. So these are references. If you are interested in have a look, and I'm sure you may have some questions. You can direct question to me, or for any VAM oxidation and utilizations, you may contact Dr. Shisu directly for further information. This is the end of my talk. Thank you very much for listening my talk today. Thank you. Bye-bye.